We are welcome to another episode on our integration. So far we've been considering integration techniques. We've done that of the substitution. I think I'm going to change my pen again as usual. We are done with substitution, we are done with partial fractions, and today we are going to take by part, integration by part. And by part we are going to look at two different categories. The general rule for by part, and then some interesting occurrences under by part. That's do with repeated integrals and then reoccurring integrals. Okay, so for this video I'm going to take the general rules for by parts, okay, and then we'll see what we can do. So let's quickly get through the introduction. I want to extend my entire slide for you. That is slide 1. With introduction or intuition for integration by part, we want to take it right from the product rule. Product rule says that I have two functions, u and then v of x. If I'm differentiating this, I have to apply the product rule in this form. You remember that I maintain u, I differentiate v, plus I maintain v and differentiate u. Now if I extend or multiply this dx here, it means I'm going to have uv, which are functions of x dx here, right? If I want to find uv, I can simply integrate both sides. Why am I integrating? The differentiation and integration sign has inverse relation, and so the derivative and the integral sign will be cancelled out. A minute. And so it means that if I'm going to integrate both sides, now I have the integral of every function here, and then my dx maintains. My derivatives and integral cancels out. I'm going to get uv is equal to, this is a sum and difference rule, so I can have it as u dv dx multiplying dx plus v du dx multiplying dx. What do you see? This and that goes away, and so I have u dv plus v du, all under the integral sign, and that is it. But we want to make from equation 2, we want to make integral u dv the subject. Making that the subject, I'm going to have uv minus integral v du. That is from equation 2. By making this a subject, and that is the whole idea for integration by parts. If we have functions multiplying each other, or two product of two functions, if it's derivative we are doing product rule, but if we are taking the integral of it, then we can do integration by parts. So know the difference here. Okay, so that is it. Let's take how do we compute examples using this integration by parts. So slide 2, we've already established this fact. It means that there will be a case where the functions will be of integral sum 0 to 4. It will have limits attached to it. If this is so, then means we are going to evaluate whatever we had with our deductions here. So assuming it is a b u dv, then it's going to be uv, the limit minus integral ab, and then whatever we have. This means that our initial function u xv was having a limit of integration. If this is the case, then this will be my new integration by parts formula. Other than that, if it's indefinite, so let me write it here. It's either you're looking at indefinite one, or you're looking at a definite integral. Okay. Now what is the rule of the game? The rule of the game is such that we have to find u, which is easier to differentiate, and we have to find v, which is easier to integrate. But you can't just look at it and then make a guess, and so we have an acronym here to help us out. That is LIAT or LIAT, however you pronounce it. It's to help you choose u, not the v. If I choose u, automatically the remaining part becomes my v or the v. So what does this acronym belongs to? The first is in order, so you choose them in order, like what we did in permutation for algebra. It is in order. So if I have an expression and then I see logs in it, so the L is this one, log or natural log, I have to choose U for that first. The I is reciprocal, then I have to choose it. The A is algebraic expression like polynomials. The T is for trig functions where I see cos, sine, tan, sec and other things. And then the E is for exponential functions. You know there are two forms of exponential functions, either this or that. So this is how I choose my U in that order. Probably you are not conversant, so you are not cool to understand this. The examples will help us out. So let's take our first example. That will be on slide 3. I want to scroll everything down for you. So slide 3. Example 1. We want to integrate x e x dx. Okay. So what we want to find at the end of the day is some integral u dv. That is what we are looking for. We don't want to forget the acronym LIAT. If we check the expression here, assuming I have f of x to be equal to x e x, what do I see? Do I see a log function in there? No. Do I see? So there's no log function, there's no reciprocal function. Is algebraic function? Yes. The algebraic function is the x. If you choose the exponential part, it is the last option for you, so you don't even have to go there first. It doesn't mean you can't choose it. You can choose u to be my exponential function, but it will become complicated when you are doing your integration. So you go by the acronym here. You can try the opposite and then see what you're going to have. So my next step is algebraic. Hooray, I have a. So it means my u is equal to x and the u. This is easy to differentiate as 1 dx, because it's like you're having the u dx is equal to 1. Okay, which means that my du, my pen, which means that my du is actually 1 dx, and we don't write 1, so it's just dx. This means that my remaining part, if u is taking x, it means that dv is the remaining part of the entire thing under the integral sign. Look at it, it's not integral u dv dx. No, there is no term like that there. It is integral u dv. It means that if u is taking this, then everything here is my dv, and so dv is ex dx. You don't leave anything out, everything. If I want v, you know we've done this, I have to integrate. Integrating exponential function, you differentiate whatever is up here and then divide. It is 1, so I still get ex. As simple as that. Okay. So now let's do a substitution. Integral u. I think I'll have to extend this writing. Where is u? U is x. What is dv? dv is ex dx is equal to u. U, we still had x times v. V is ex. We will take away this bar because it is an indefinite integral, minus integral v. V is ex du is dx. Yeah. So that is what we have. So next, try to simplify this. I have ex minus. If I integrate ex dx, what do I get? We've already tried this integration from above, and it's simply the same as this dx, and so plus c, because it's indefinite integral. If I factorize ex out, I'm going to get x minus 1 plus c. This is my solution. That is the answer of the day. That's how simple integration by parts is. So example 2, you know I always give you 3 examples. So example 2 here on slide 4. I want to integrate x squared 4x dx into something like this. And don't always forget the LIAT. So the function, do I have a log function? Yes, so automatically I end there. It means my u is ln 4x, so ln 4x, and then my dv becomes the remaining x squared dx. If I take just this part off, I'm left with this and that. So I told you don't leave things out. Okay, so what is du? If I differentiate ln, I'm going to get 1 over x. dv, if I integrate that, I'm going to get 1 over 3 x cubed. Yeah, that's what I'm going to get. We've gone through fundamental integrations and differentiations, so I always want to write my final answer. Let's do substitution. U is okay, so u is ln 4x, and then dv was x squared dx. So it means I can rewrite this thing as, anyway, let me just leave it for now, x squared dx. I can rewrite this to make it look nicer and make it x squared ln 4x dx. It's the same thing, it's equal to, now my u, we had it as ln 4x, my v, what did we have, x 1 over 3 s cubed minus integral v is still s cubed on 3 times du. Du is 1 over x dx. So I missed this out because I'm differentiating with respect to x. Okay, so this is my u. Now du becomes 1 over x dx. Now we can simplify this down, and this is going to give me s cubed ln 4x all over 3 minus, this cancels this and I get 1 over 3 out, integral s squared, it cancels one of this dx. Okay, so this is same as s cubed ln 4x all over 3 minus 1 over 3. If I integrate s cubed s squared, I'm going to get this, and this simply gives me plus some constant of integration, like whatever is here, minus 1 over 9 s cubed plus c. That is the final answer. So it means that the integral s squared ln 4x dx, which we were looking for, is actually this. Let me go back to example 1 and then rewrite the final thing. Well, yeah, okay, so I have it that here. So example 3, I hope it's been cool to cooperate. We want to integrate this. Why we use integration by part? Because I have f of x and then I have g of x in this form. They are multiplying. I'm assuming this f of x and then everything here is g of x. So if I'm using my acronym here, do I have a log? No. Do I have inverse or reciprocal? No. Do I have algebraic expression? Yes. So I move to that. Which one is algebraic expression? I'm going to use x, like the polynomial. Okay, and then what will be my du? Let me write dv first. If u is this, it means dv becomes x plus 1 to the power half, or dx, everything remaining. So the u becomes the x, you know that, and then v, I have to integrate this. I'm going to integrate x plus 1 to the power half. You know you have to add 1 and then divide by that, and that's 3 on 2, so I'm going to get 2 on 3x, half plus 1 is 3 on 2, plus some constant c, whatever you want to do. Okay, so let's do the substitution. So it means I have integral of u, which is x, and then dv, which is x plus 1 half dx. The original equation will be equal to u, which is x, v. What did we get for v? We had 2 on 3 x 3 on 2 minus integral u, we still had x, dv, we had I hope I'm doing the substitutions well. dv. I think I'm messing something up. Yeah, here I'm not done. It is x plus 1. Yeah, 3 on 2. Okay, so let me do the corrections. This is x plus 1, 3 on 2, minus integral u, which is still x, and then dv, which is 2 on 3. Oh no, dv x plus 1, 3 half. Yeah. Why is it so difficult for me to just get this thing done? I think I know what I've done wrong here. This is v, the u. I've just mixed these things up. That is why. Yeah, it makes sense. Let me check the other ones if I didn't make such a mistake. It is fine. Example 1, it was also fine. So I messed up for example 3. Yeah, it's good I corrected myself. So integral v is 2 on 3, x plus 1 to the power 3 on 2 times the u, which we had just the x. So now let's expand our right hand side. This is going to be 3 on 2, or I get 2x on 3, x plus 1 to the power 3 on 2 minus integral. I can bring 2 on 3 out here, so I can just integrate x plus 1 to the power 3 on 2 dx. And doing that, everything here maintains, minus 2 on 3. The integral of this part becomes x plus 1. 3 on 2 plus 1 is 5 on 2. All over 5 on 2. That will be 2 on 5. Plus a constant c. So my final answer will be whatever I had here, which is 2x on 3, x plus 1 to the power 3 on 2 minus that will be 4 on 15. Why? Because I have 2 on 3 dividing, so multiplying 2 on 5, x plus 1 to the power 5 on 2. Okay, and so that's 4 over 15, x plus 1, 5 on 2 plus c, and there's the final answer. Okay. So you want to try it out, and then see what you're going to get. In the next episode, we'll take the remaining 2 techniques, that is and so on, that by part, when you have to apply integration more than once and when there's recurrence. Please try hands on this, and then so we know we don't have integral of ln x in a direct tabulation. What we know is that if I integrate 1 over x, I'm going to get ln x, and if I differentiate ln x, I'm supposed to get 1 over x. There is no integral of ln x, so what can you do? We can still use a product integration by part. How? If I set, I'm going to use Layat, right? Or Layat, however you pronounce it. Do I have a natural log? Yes. So it means I'm going to set then u to this, and then it means my dv will be left to just dx. As simple as that. It's as if I have 1 here. And so find your du, find your v, and then do the substitution. Thank you very much, and see you later.